Okay, well, I have a proposal. I would like, if in case someone wants to see a second example of how to do the proving the correctness of loops, I have another example that I can go through, but I don't want to take the time in class to do it because we need to move on. Post a video of just, the second example. It'd be kind of boring, I think, to do the exact same thing again. I'll have the video. Okay, so, and I guess the homework due today was a correctness of loops problem, right? Did that work out all right?
Yeah, just fine.
Okay, so good. So that means that the supplementary, going through yet another example, would be kind of nice just to do it not in class. Okay, well, good deal. All right, now, today we are starting another really big topic. We are going to look at the theory of relations and functions. The first thing that we have to learn is the concept of an ordered pair. Okay, so,
Sounds familiar.
you've heard this before? So here we have an ordered pair. Now, I want to give you an example. You know how your English people always want you to compare and contrast when you write an essay. So let's compare and contrast ordered pairs with sets. So check this out. What do you know about these two sets? In other words, here I have a set 2, 3. Here I have a set 3, 2. What do you know? And so this is a set. This is curly braces a set. So
Don't have index, do they?
They're the same element.
well, haha. They have the same elements, but you're saying they are equal. Okay? So this set equals this set. Right? Because in sets, the order doesn't matter. Right? It's just you can list them in the brace in any order, right? So in sets, order does not matter. Okay, that's contrasts with ordered pairs, because the reason you call it ordered pair is because first and second, it's ordered. Yeah, it makes a difference. So if now the notation that we use for ordered pairs is instead of using braces, we use angle brackets. So ordered pair 2, 3.
So it looks like a hint or?
Yeah, it actually looks like a hint. So just by the context, you have to know which one it is.
So that's not an ordered
So this is an ordered pair, and this is an ordered pair,
not equal.
but they are not equal. Okay, so this is an ordered pair. Okay, so that's the distinguishing feature of an ordered pair compared to a set, in contrast with a set. And here, if you want like a geometric representation of ordered pairs, you can think of these as being coordinates. So here, this would be x coordinate and y coordinate. So if this is x and this is y, then this 2, 3, this is x equals 2, y equals 3. That x equals 2, y equals 1, 2, 3. So this ordered pair would be here, right? So this is 2, y equals 3. So this would be the ordered pair 2, 3. And this point is not equal to this point, because this point is, here's 3, and here, oops,
There's y.
this is 3, and this is 2. You're right, I did. And this is ordered pair, and this is ordered pair 3, 2. Okay, so those, not the same point. All right, so let's wait a minute. If these ordered pairs are not equal, the first thing we have to determine is, what does it mean for two ordered pairs to be equal? And what do you think?
They have to be equivalent.
Well, what does that mean? What does it mean to be equivalent? Yeah, it means the first one has to equal the first one, and the second one has to equal the second
Is there
one.
any notation for location within an ordered pair? Like,
No.
Like vis a vis.
No.
just curious.
Yeah.
You could do a computation.
Yeah, no, this is not like an array. It's an ordered pair. Okay. Now, so let's take a look now then at our very first axiom. Our very first axiom defines what it means for two ordered pairs to be equal. And what does it mean? So for ordered pair BC to equal ordered pair B prime C prime, what does it mean for them to be equal? What has to be true?
B.
B equals B prime and C equals C prime. Okay, does everybody understand then? That's 4.2. So anytime you want to talk about ordered pairs equal, 4.2 is what does that. All right? Now, 4.2.1 is the ordered pair 1-point rule. Now, what's interesting about this is that you're going to prove it. Okay? But, how do you prove that two, ordered pairs are equal? Well, you use the axiom pair equality, see? So now what does the ordered pair, let's take a look at what does the ordered pair 1-point rule say. It says provided that X and Y doesn't occur in E and F. Okay? It says, now, what did we normally have for the 1-point rule?
Can't you just use the 1-point rule?
Well, yeah, you do.
That's one step.
That's how you get E
That-
all out of the quantification.
That's one step.
Well,
Yeah.
no, it's not one step. Because what you have to do is, in order to use the 1-point rule, see, because the 1-point rule doesn't deal with ordered pairs. So let's think about how you would prove the ordered pair 1-point rule.
Do math.
1-point rule.
No, you can't do the 1-point rule because it's an ordered pair. So you can't use the 1-point rule.
Pair equality.
But what does it mean to have pair equality? So X comma Y equals E comma F, that would be what?
B equals, or X
E
equals
is
F
E-
and Y equals F, or
X
X
equals
equals
E,
Y equals
and, but so now how are you going to deal with that and? And how are you going to use the 1-point rule? Because so now that you have individual numbers, no.
Demar's.
This is really funny.
What's the bar mean?
Oh, look, that's star X comma Y. That's the range. The bar separates the dummy from the range.
Oh, it's actually like a quantification.
It is a quantification. Yeah, this is a quantification. So what quantification principle can we use?
First.
Yes.
Rating.
With regular, because all these regular generals of quantification,
Yeah.
they have one dummy for the most part.
For the most part, but which ones don't have just one
He
dummy?
wants to use that one, nesting.
Nesting. Aha. Very good observation. Very astute. So what you do is when you nest, then you can get it. But then in order to nest, there's a proviso, right?
Sure. Well,
But unfortunately, this has the proviso. So we can use nesting, right?
What if it didn't have the proviso?
Well, but it has the proviso, so we don't have to, well, that wouldn't work.
Well, then we couldn't use it at all.
Right. It has the proviso, okay? All right, so, yeah.
Gets you to the 1-point rule?
Yeah, and then once you use nesting, then you're dealing with it with just one point instead of 1 point instead of an ordered pair. That's how you get the 1 point. All right?
So let's do this.
Well, no, that's for homework. I'll let you do that.
Wait, we have to prove this for homework?
Yeah, you have to prove it for homework.
Fun.
But now I just gave you some
That's a big
tips. All right, gave you some tips there. So the tip is use nesting and use the definition of ordered pair, and then once you use nesting, then you can use the ordered pair 1-point rule. Then you can use the regular 1-point
Do you
rule.
have to do it twice?
Yeah, you have to do it twice.
And then you have to combine the textual substitution?
Yeah, how do you combine the textual substitutions? Because, a property of textual substitution, but there you're going to need to do the occurs as well, because of the occurs. Yeah, you know the provisos, and so you can combine them. Oh, very good. You guys
Is
are
there a
good.
theorem that combines them? Or we just,
No, property of
Well, you
textual
know that
substitution.
You can because of that proviso.
Yeah,
right. I
because you'll have one textual substitution followed by another textual substitution. But as long as this doesn't occur in here, then you can do them at the same time. Yeah? Okay, so that's ordered pairs. Now the next thing we want to talk about is the cross product. Have you ever heard of this?
Heard of it. Don't know what it does.
All right, well here it is. The cross product. Now, 14.3 is axiom cross product. And what does it say? Now first, in 14.3, 14.3, we have to understand that S, capital S and capital T are sets. Okay? They are
Program
sets.
statements.
No, they're not. Oh, yeah, right. We're not. No more. They're not program statements anymore. We're done with the theory of programs. So now capital S and capital T are always going to represent sets. All right. And let me just give you an example. Let's suppose that S equals. Let's suppose that the set S is this set. Suppose it's the set A, B, C. Now this is a set, so order doesn't matter, right? Okay. And suppose that T is the set 4, 6. All right. Now, can you tell me, based on that definition right there, what is S cross T? Now let's see if we can read this, and can somebody tell me what that is? Well, first of all, what's the first thing that I write down? It is a what? It is a set. Right? So this is going to be a set. But let's enumerate this set. With this example, let's enumerate this set. What is it a set of?
Values?
No.
Set of sets.
No.
Ordered pairs.
How do you know it's a set of ordered pairs? Why did you know that? Because in the body, what does it have? An ordered pair. So this is going to be a bunch of ordered pairs. And which ordered pairs is it going to be?
The ones that are in both S and T.
Well, look at what it says. It's a set of ordered pairs B comma C. But how do we pick the B?
B is an S.
B are the well, no. The B's are the what?
Elements of F.
And the C's are the element of what? T. So what is it? So what is this set of ordered pairs?
A4,
Yes.
B4, C4.
A4, B4, C4,
And then
B4,
A6,
H6.
B6, C6.
A6, B6, C6. We could have done these in any order. Excuse me, wait. Before.
Not true.
Now, I mean, what I'm saying is, we could have done the ordered pairs in any order, but within the ordered pair, it matters. We could have written the ordered pairs in any order, because those are a set. But it's a set of ordered pairs. Yeah, so now are we good about this?
Not really.
Why not? What do you not understand here?
No, I mean, I understand that, but I had to come up with that using that. I did.
We just did. We just came up with this by looking
I'll
at
go
the...
around. Go around.
Oh, I'll go the other way around. Oh, yeah. Well, yeah, we won't ever have to do that. Like if I give you this, then how would you quantify that way? Yeah, no, we won't ever have to do that.
Okay, so we have to understand it.
But going the other way, you definitely should be able to do that, right?
How do you know that every element matches up with all the other ones?
What do you mean everyone matches
For all
up with
B
all?
and C,
It's for all,
well, set.
it's in the range. It's in the range B is an element of S and C is an element of T. So anytime you quantify, it's all the possible ones that make the range true.
Okay.
It's all the remember how that's how we always do the quantification. It's all the values that make the range true.
Okay.
So these each one of these makes the range true, and there's no other ones that will.
But we're not quantifying it, it's just a set.
Well, but we're using the set. Remember the two ways to do a set. One was what?
Fine.
One was enumeration, which is
Right.
this, and then what was the other one? What was the name of this one? Do you remember? Enumeration and what was it here?
Is it abbreviation?
No.
Comprehension.
Yeah.
Ah, good.
So this one's a
Set, yeah, set comprehension. Did we say comprehension here anywhere?
I'm not just.
You know, actually, I don't think it does say it on the
But it is.
yeah, but it is set comprehension. Okay. Now, so let me give you another example. What is? Do you remember what this set is? This is the set of real numbers, right? So 0, 0.1, 0.2, negative 0.1, negative 0.2.
Is it just the two?
No. It's no. It's that was just example. There's an infinite number. I don't have time to say them all. But tell me this, you guys. What is this?
Oh, man.
What is this cross product?
True.
No, it's not true. What is this a set of?
R.
No.
It's a set of
Of-
ordered pairs.
It is a set of ordered pairs, and the first
Oh,
one,
that's good. Too many.
it is a lot. It's an infinite number, but it's a set of all the ordered
It's more
pairs.
infinite than each one of those.
Yeah.
Where the first one's a real number.
Where the first one's a real number and the second one's a real number. So basically, geometrically, what is it?
Whole
It's
plane.
a big black plane.
Yeah. This is a set of all the points on the plane, right?
That's
Set of all points, because we said, a point, we did the coordinate,
so it's
set of all,
U. It's U, right?
R cross R is U.
well, it could be if you, yeah, it could be if you're talking about the universe as being, yeah. Mhm. All right, now let's take a look at let's take a look at 4.3.1, talk about that for a minute. This is ordered pair extensionality, okay? Now, okay, so now what is U?
It's not universal.
No. It doesn't have, it's not bold with the little, so this U, so what is the type of U and what is the type of V? What do you, they are, but what are they, that is correct, they are sets, but what are they sets of?
Ordered pair.
Yes, so in 14.3.1, U and V are sets of ordered pairs. Okay, and what is it that we're claiming? What is it that we're defining here?
That every ordered pair is ordered.
Well, what is it on the left-hand side of the equivalence? What are we claiming as equal? What are we defining as equal?
It's just a-
Yeah, but what are they sets of?
Ordered pairs.
Ordered pairs.
Each
So
ordered
this is
pair
what it.
exists in one, exists in the other as well.
Yeah.
Boom.
It doesn't have the set. They don't have to be in the same order, but within them they do.
Yes.
Jordan pairs.
Yes. So, but this is defining what it means for two sets of ordered pairs
Right.
to be equal. Are you with me?
You got it.
So, like for example, suppose U is this set. Suppose U is this set 1, 2, 1, 3, 0, 5. All right? And suppose V is this set 1, 2, 1, 3, 0, 5. Are these two sets of ordered pairs equal?
Yeah.
Obviously they are, but why is that? Because why?
Every
For
ordered pair
all
exists in one.
x, y. Now notice that this isn't for, this is double quantification. For all x, y, range true, x, y is an element of U, equivalence, x, y is an element of V.
So either it's true or false.
So that's either true or false. So these two, because this 1, 2 is in here, so therefore 1, 2 is in here. 1, 4 is not in here. 1, 4 is not in here. Right?
They could be in any order though, right?
Well, yeah, within, okay, but not within the,
Well, not within the ordered pairs,
right,
but-
exactly. Yeah. So this is ordered pair extensionality. This corresponds to extensionality that we had for sets.
What if there was like two ordered pairs within U that were the same?
Aha! Good question. Suppose we had this 1, 3, like this.
Still equal.
Do you remember that with sets in general, we had this property? We said this set, that's even easier yet. We said that this set, AA, we actually proved this
Oh,
once.
yeah.
We said that this is A, right?
Because of the or.
Yeah, because of the OR. So duplicates, duplicates are redundant. So this is the same as, so this set is the same as this set, and it is equal to this. Oh, that was a good, nice recall. Nice question. So everybody, are we all good? These are reviewing all these good properties of sets and everything. We're just making them sets of ordered pairs now. All right. So now let's take a look at 14.4. These are theorems now. So guess what we can do with theorems? We can prove them, and guess what you're going to do with 14.4? You're going to prove it for your homework. So what does it mean? What is it? Theorems for cross product. What does it mean for x comma y to be an element of S cross T?
That's the one I was looking at when you didn't.
It's like
That-
14.2.1.
Yeah, well,
That ordered pair is
So
in
easy.
that cross product of the set.
that equivalence, x is an element of S and y is an element of T, right? So, and then, so 14.4 is a homework problem. 14.5, what is 14.5? That says ordered pair xy is an element of S cross T, equivalence ordered pair yx. So this is switching the thing,
I'm switching.
but that is an element of T cross S. So you switch that as well. So here,
That's pretty obvious.
yeah, it is obvious, but it's going to be based on
That's all
some.
homework?
It's going to be, yeah, that's a homework problem. 14.5.
Gimme
Okay.
3 points.
Okay. And 14.6, let's take a look at 14. I won't ask you to prove 14.6, but let's take a look at it. S equals the empty set. So now, and what is S? It's a, is S a set of ordered pairs?
Yeah.
No. In this case, it's not, because what we're talking about is S cross T is the set of ordered pairs, right? So if S is the empty set, that implies that S cross T equals T cross S, and T cross S equals the empty set.
There's no
You say there is no and. Was I wrong? Was I wrong there? Was I wrong?
No, it's equals.
Because why?
Conjunctive.
The conjunctive meaning of equals. Huh?
Rookie mistake.
Okay. Okay. And 14.7 says S cross T equals T cross S. Oh wait, how can S cross T be equal to T cross S?
If S and T are the same.
That equivalves either S is the empty set, or T is the empty set, or
They're the same.
S and T have to be the same set. So if you cross them, that, yeah. So that's a theorem. I'm not asking you to prove that, but it is,
Sick.
okay. It is not sick, it is well. All right. Let's take a look at 14.8. Distributivity of X over union. And you remember what the remember what union is? The union of two sets?
We gonna do all of set stuff.
Okay, so yeah, this is all sets, but this is all sets of, this is a set of ordered pairs. So you're gonna have to go back and use all those theorems that you would use for sets. Okay, so isn't that wonderful? Okay, so hold on. So let's suppose T is the set, you know, A, B, C, and U is the set A, D. Then what is T union U?
A.
B, C, D.
A, B, C, D.
Oh, I was thinking intersect.
Yeah. Okay. And what is T? Okay, we'll do intersect. So, and what is T intersect U?
Just A, right?
Yeah.
Just A. So that was, remember, that's how union and intersection works. And 14.8 says, now what is this an equality between? See, T and U are set. S and T and U, those are all sets. So what is this equality between? Is this equality between elements?
A set cross set and a set of ordered pairs union with a set of ordered pairs.
But isn't there a cross in that one as well?
Yeah.
So what are these sets of? What are S and... So, sorry,
They're
I'm sorry.
all
So,
sets of ordered pairs.
yeah, the equality is between sets of ordered pairs. Now, this... what I'm going to do now is show you an example of how you prove sets of ordered pairs are equal, all right?
Let R be an arbitrary.
Yes.
Yeah.
That's what we do. But now what we have to do is we have to use, and I didn't bother to put this on the equation sheet, but you have to use the same thing that we did for,
Lemma.
yeah, the 9.8 lemma.
Homework.
Yeah, we had to do the 9 point, we used the same technique of proving the 9.8 lemma, but instead of doing it with elements, we do it with what? Ordered pairs. So it's the ordered pair version of the 9.8 lemma. Are you with me?
Alright, it's still very similar.
Yes, it is. So here, let's look at 14.8. 14.8.
So is this the
The-
14.8 level?
This is, yeah. Well, I mean, no, this isn't it, but we're going to use that technique. I didn't write up the 4.8, I didn't write up the ordered pair version of the 9.8 lemma. But I think we'll do it here, and it's legal to do it.
And we
It's-
still only have to do the lemma, not
and you still just only have to do the lemma, right? So anyway, so 14.8 is a set equality between sets of ordered pairs, And what you do is you use the technique of proving the 9.8 lemma. Use the technique of using,
proving.
of proving, yeah, that's good. Of proving the 9.8 lemma, but with ordered pairs, all right? So what we're going to do now is let's prove 14.8a. So here we go. Proof of 14.8a. So we'll do the first one. All right, now, you guys.
Let
Yes.
A, B be an arbitrary.
Yes, that's exactly what you do. We're going to use xy. So let's say we say let xy. Instead of saying let x be or let x be an arbitrary element, we say let xy be an arbitrary what? Ordered pair. Okay? And then prove the 9.8 lemma. And prove the 9.8, yeah, 9.8 lemma, which is what? So now what do we have to prove?
X, Y is an element of the left and an element of the right.
Yes. We have to prove that x, y is an element of, now what's the left? S cross parentheses T union U, S cross parentheses T union U. Now what is this? Now what comes?
Equivals.
Equivals, because that's a Boolean. It either is or it isn't. So these are, right? It's a Boolean expression. Equivals what?
S cross T.
Xy.
Oh, right.
Ordered pair xy is an element of
S cross T.
S cross T
Union S cross U.
union S cross U. Should we start with the left or the right?
Right.
I think we should start with the left.
I think we should start with the left.
You want to start with the whole thing? Now let's start with the left. Let's start with the left. Okay, so let's go. X, comma, Y is an element of S cross T union U. Holy moly. What in the heck are we going to do with all of this gobbledygook?
Do the
Prove what is,
Go back
what
a
is it
page.
mean?
Go back a page. Let's go back a page.
membership.
I think membership is right.
It is.
That'd be-
Yeah, that's the only thing we have.
It is the only thing we have. This proof virtually writes itself. I mean, we can just put this on autopilot, and there's only one thing we can do, right?
I think the other ones are very similar.
Okay, yeah, they are. Okay, so now, but as long as you get these concepts down, you know, what is,
Four, so we have X
So
is
for-
an element of S
X is an element of S, and
Y is an element of T union U.
Yeah.
Y is an element of
I'll explain.
T union U.
Oh, I know Theorem we could use.
And now we have to go way back.
What is union?
Push them back, push them back, way back. Ooh, did you hear that?
Chapter 9.
Yeah, I'm on 1120 and then distributivity of and or.
11.20, axiom union. I mean, that's the only thing we can do, right? I mean, well, what can we do with this? 11.20.
Break it down.
So this, break it down. So this is 11.20, the definition of union. So what do we have here then,
X
folks?
element S
Okay, X is an element of S.
and Y element.
And
Y
what?
element T or Y element T.
But now we have an and with an or. So what?
Y element T
Y is an element of T,
or
or what?
Y element U.
Y is an element of U. And now,
We flip them around.
Do math.
Distributivity.
Of and over or.
of and over or, distributivity of and over or. So this equals by distributivity of and
346.
over or, which is, which number is it?
3.46.
3.46?
X element S and Y element T or S.
Okay, so let's move over here. So tell me what this is.
X element S
X is an element of S,
and Y
and
element T
Y is an element of T,
or
or X is an element of S,
I don't know the last part.
And y element of u.
and Y is an element of U. You were kidding, right? Okay, you guys. Now, back to the future. We did skip back here. It was time travel. Okay, so now what?
14.
How many times? Twice.
So many times.
14.4 twice. Gives us what? This gives us,
Oh, we're back
this gives us,
in. X is an element of
no. X is an element of S and Y is an element of T.
Ordered pair xy.
Ordered pair XY is a what?
Element of
Is an element of
S cross T.
S cross T, okay,
or
or
ordered pair xy.
ordered pair XY
Of
is an element of
s cross u.
S cross U equals by what? Oh, this proof writes itself. I know, I said it again for emphasis. So what is this?
What we want it to be.
Tell me what it is.
X, Y,
XY
element of
is an element of
S cross T union S cross U.
S cross T union S cross U. And boom, just like that. So put that in your pipe and smoke it.
Yeah.
All right, good? Okay, so now we've learned, so let's recap. We introduced the concept of an ordered pair, then we introduced the concept of a cross product, and then we have this concept of sets of ordered pairs, right? Now, all of that is leading up to the main
Bless you.
topic, which is relations.
He's like bleeding.
Oh, hey, you guys, check this out. I'll let you read. I'll let you read over these, but check this out. We have a monotonicity theorem.
Oh no!
Look, 14.11 monotonicity.
Yeah, they announced it all.
All right. So next topic is relations.
You just skipped over an entire page.
Yeah. I was pointing out some things, although I didn't have everybody's attention. It appears. We have a monotonicity, and then here's. Oh, we should think about this. S is a subset of U and T is a subset of V, implies S cross T is a subset of U cross V.
What's the definition of pound?
That's 14.12.
What are you doing? 14.14.
Well, I mean, all of these are theorems that you could prove. I don't think I'm asking you to prove any in this group, but you can. We can read through them and see that they make sense, right?
Yeah.
I mean, S cross T is a subset of S cross U, and S is not the empty set. That implies that T is a subset of U. That makes sense, right? Oh, and here, how about this? For a finite S and T, do you remember what this pound sign was?
No.
The number of elements in.
Yeah.
So what is the number of elements in S cross T? Remember we had that example of S is ABC, ABC, and T was 4, 6. Remember that? So the number of elements in here was 3. The number of elements here is 2. And if you, when we wrote it out, it's 3 times 2 is 6. Right? Yeah? All right. So let's do relations now. Everyone wants to have good relations. Yeah? But mathematical relations are a little bit different from personal relations.
Probably really boring.
And I want to introduce this with an example. So consider S is 0, 1, 2. Now, here is a situation that happens frequently. Up until now, we've been doing S cross T, and S and T can be 2 completely different sets, like the example we just had a second ago, where S was ABC and T was 4, 6. It frequently happens that you cross the set with itself.
Whoa.
Now, what is S cross S? If S is the set 0, 1, 2.
0, 0, 0, 1, 0, 2.
Yes.
Just a mess, basically.
How many elements?
9.
Correct. 0, 0, 0, 1, 0, 2,
1, 0, 1, 1, 1, 2.
1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. Does everybody see that? Okay. Now, I want you to consider the less than relation. Okay, so consider the quote less than relation. All right? Now, I'm going to throw this concept on you now. See if you can get this. A relation, this less than relation, is going to be a subset of this set of ordered pairs.
Yeah, I didn't get it.
So consider the less than. My statement is it is a subset of this S cross S. It is a subset. It is a subset of S cross S.
I would agree with you. Tell me what this is.
Well, can you surmise what it is? Consisting of all, but what is S cross S? It's a set of what? Ordered pairs, right? So consisting of all the ordered pairs, consisting of all the ordered pairs that have what? That
Less than.
all ordered pairs X, Y, for which what?
X is less than 1.
Yeah, because it's the less than relation. For of all the ordered pairs, X, Y, for which X is less than Y. Are you with me? For which S is true. I'm saying that's the definition. We're talking about definitions here.
So this
Notice
is
that this says definition, binary relation. A binary relation over B cross C is a subset of B cross C. I'm claiming that the binary relation less than over this set is a subset of this. Okay, so
How do you know that X, Y?
this is by definition. Well, that's X less than Y is not true. Look, ordered pair X, Y, X is less than Y is not true for all of these ordered pairs. It's only true for a subset of these ordered pairs.
0, 1, 0, 2, 1, 2.
Exactly.
That's it.
That's it. Okay, so here we're going to write this. Less than, okay, here. So now,
Greater than.
yeah, binary relation, less than or equal. Yeah,
Any one of those.
yeah. Okay.
Binary infix operator.
Okay, so look. So this less than relation is equal to what set? You just named them.
0, 1, 0, 2.
0, 1, 0, 2,
1, 2.
and 1, 2.
So that's the less than relation?
This is the less than relation over the set S cross S.
flip those.
Actually, we normally abbreviate this and we say this is the less than relation over S, and we mean S cross S.
Flip all of them and you get the greater than.
Yeah, good point. Now, does everybody see that how that works? Does everybody see how that works? And get the equals relation is what? 0, 0, 1, 1, 2, 2. The less than is,
Greater than is the bottom left corner.
yeah, right. So remember, this is an important point. Remember, and this I'm going to put in words what 14.15.1 is. Remember, a binary relation is a set of ordered pairs. A binary relation is a set of ordered pairs. That's what it is, sports fans. And we're going to emphasize that by putting a big blue box around it.
Relations, one of those places as well. At the relations symbol.
Oh, this is the less than relation,
Oh, right.
right? In this particular example, okay?
Less than equals. Wait a second.
Are we good? Now, the next thing we want to learn is there's a way to do this pictorially. So let's go over to the other side of the room and draw a picture of that less than relation. Now, here's how we picture that less than relation. What you do is yeah, it is a graph. So this relation can be represented by what's called a directed graph. Okay, and what you do is we'll put 0 here. Whoops. We'll put 0 here, and we'll put 1 here, and we'll put 2 here, right? And what you do is everywhere there is a ordered pair from x to y, you draw an arrow from x to y on the graph. So the 0, 1 is this arrow. Are you with me? And the 0, 2 is this arrow. And the 1, 2 is this arrow. So this is a picture of the less than relation.
Okay.
All right? Are we good?
What's the picture of S cross X?
Oh, what is the picture of S? Yeah, let's do that. 0, 1, 2. Since you asked, what would it be? It would be here, 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 here. Well, does it?
Yeah.
Here, 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 and here. So this one is S cross S.
Completely.
Are you with me? In fact, let's take a look at another one. Definition identity. The identity relation IB on B is IB equals a set of all X on B, range true, body what?
False.
No. Body what? 14.15.2. XX. So tell me I sub B. What is I sub B in this case? What is I sub... Now, this B, well, this B is... in this particular example, it's I sub S.
Identity relation is the equals relation?
No. What is the definition of a relation is always a what?
Subset.
Of what?
Cross product.
Of ordered pairs. So what ordered pairs are in the identity relation?
Identity of what?
S, the identity over the set S. This example that we did. Say it again?
0, 0, 1, 1, 2, 2.
Exactly.
But so it is the
0, 0, 1, 1,
That's the idea.
2. Because by definition. It says here, the definition, identity. The identity relation B on big B is I sub B equals all the set of all x's in B, range true, body x comma x.
isn't that the
So here it is. For if the B is S, in this example, S is the set 0, 1, and 2, then the identity relation is 0, 0, 1, 1, 2, 2.
Isn't that the exact same thing as the equal values by the equals by-
It is the same as the equals. It is. Okay, does everybody see how that works?
Yeah.
Okay?
Leave that
That's
one.
it. Sports.
It's the exact same thing.
Oh, we're out of time. No idea.
Okay, oh, and let's just draw this before we quit. How would we draw this one?
3 separate numbers going to
0, 1, and 2, and it would be like this.
Does it have to be an equilateral triangle?
No. So there, we drew that picture, right? What about the empty relation?
So it's
Do
just
we
the
have?
numbers and nothing else.
No such thing as an empty relation.
Yeah. It's, what is it?
No.
It's the empty set.
So you just draw the numbers and then nothing.
And nothing, yeah.
But you don't draw any numbers, right?
Yeah, ABC, the empty.
You can draw a 0 and 2, but then there's no arrow thing.
Right. Okay.
Will we ever
Now,
use that?
14.15.3, the identity lemma, 14.15.3 is a homework problem.
Yay.
Good to know.
But the curiosity, how can
There be no relation with something that has stuff in it.
It's called the empty relation.
They don't really.
You can look for a relationship between a bunch of different numbers that none of them satisfy.
And none of them are, yeah.
It would be
I mean, by definition, the empty relation is the relation with the empty, it corresponds to the empty set.
So there won't be.
So none of the numbers are related to any of the other numbers, according to that relation.
Bunch of lows.
The relation is they're not related.
Yeah, the relation is they're not related.
when put together.
And on that note, I'll see you next time.